Yes, please.
Okay, thank you so much for the nice presentation.
Mm,
And the basics are now very clear to me. And
uh,
I have a question from the basics, maybe the slide number 6, which is just the previous of it.
mm, yes.
No, maybe I just missed read it. Where you shown the graph, where you shown the, yeah, here it is. This is
Mm,
so I want to know about the Gibbs free energy, which you have just shown here. So I
mm.
want to know that on works, what circumstance the Gibbs free energy of the reaction in specifically into the catalysis field it depends upon.
Ah, Basically, in the field of the catalyst, we play through the electrons. So, as an example, so maybe I can clearly explain from this slide. So, like here, so under a ordinary condition, so here is we need this molecule needs around 795 volt, 800 kilojoule per mole energy, activation energy to be converted into some other product. But basically here, if we just play through the electrons, like this molecule is a linear molecule. So here is a partial negative, here is a partial positive. So principally it should have some dipole moment, but in dipole moment we have a sine theta. So this is one angle of 180. Sine of 180 is 0, so dipole moment is 0. So in the field of the catalysis, we play through the electronic structures. So if we will provide some electrons here, and it will distort its structure. So if electron will be there, according to valence shell electron pair repulsion theory, so this electron repel the bond pairs, and this bond pair will be tilted to the smaller angle. Then this angle will be like 150 or 130 or something like this, 160. So then sine 160 will give some value. So that this value will correspond, will generate some polarity. And then under, if this molecule becomes polar, so even we give a less energy, it can be converted into some other compound. So this is how basically we play with the catalysis through electronic modification. And then first we this stage is called activation. First we activate the molecules, and then we convert it into some other product. So this is how in catalysis we overcome the Gibbs free energy of reactions.
Okay, so basically it depends upon the so can we play with this something like the temperature or maybe entropy of the system like this?
Of course, like even if we do not apply any catalyst there, so this molecule CO2 can be converted into some other product at 800 degrees C with the help of hydrogen. But what we do, we introduce some catalyst, and then it can be converted in a mild condition like 250 or 350. So of course, if we do not use catalyst and we play with some temperature, pressure, and some acid-base equilibrium, this kind of stuff, so of course we can play. But usually we want to reduce these conditions by applying small amount of the catalyst to reduce the overall cost. So this is how we want to do in the field of catalysis.
Thank you so much. It's crystal clear now.
Thank you. Thank you. Mhm.
Can I have a question, Asif?
Yes, please.
Thank you. Presentation.
Mm.
I want to comment or need a little clarity on the relationship of the surface area with the active sites. With the yeah.
Yes.
Um,
So thank you so much, Professor, for a nice question. So your question is, what is the difference between the surface area and the active site, basically?
hmm.
So basically, if we want to know about the surface area, in surface area, we will consider this
May,
site.
may I may I repeat a question?
Please, please.
What you stated, higher the surface area, lesser the activity. It may happen,
Yes.
but on what grounds it happen?
Yeah.
Uh,
So
is there any role of no uh, is there any role of electron donating or accepting surface active sites on the same material?
Yes, yes. Actually, so first we have to find like what kind of active site we need for our reactions. So either it's electron donating or electron accepting and whatever it is. So first we decide, and then we have to go into the like we are using if inorganic material or some organic material. So we have to go to the atomic level, like which atom, like in an organic structure. So usually we go to the which like atom is a active site. In an inorganic site, we go for the crystal structure. So which crystal site is active for our reactions. And then like if we have here many active sites, if we have here like in this particle we have many sites, but problem is like each site is not active for our reaction. So if our one site is active for our reaction, so this will count to the active surface area, but all other sites, this will go to the just surface area that we measure from the BET. So in BET, basically, we measure to the N2 sorption methods. So it cannot distinguish between the active site and non-active sites. So it will measure the overall surface area of the material. Then we have to find like in our materials, how much fraction of that surface area is active for our reactions. Then we can calculate our active site surface area. So this is how we want to play. Like all the surface area is not active for specific reaction. So this is how we always have some side product. And this is also very difficult to control it. Like if like for a CO2 hydrogenation, if we have a iron oxide 111 is active, so why we cannot produce, why we are not producing just 111? But this is very difficult and actually unavoidable situation. Like we cannot produce only one crystal phase. We of course we have other crystal sites as well. So but we want to maximize it, and then the other site which are active for the side product, so we want to minimize it. Like this is a famous example for a cobalt based catalyst. So basically terrace site is active for the methanation, and methane selectivity is around 70%. So many people are working and they publish in Nature Science and very big papers. So they want to kill that terrace site. So sometimes we want to have an active site, sometimes we want to kill some active site just to get a specific sites that only accelerate our reactions. So this is how we want to play with the active sites and we get the maximum yield. Is it clear?
Yeah. Yes. But another uh, little question is, can we found both accepting or donating electron active sites on the same catalyst surface?
Basically, this is very good point. Like people are working on that. Like people are trying. Like, of course, when there is a electron donating site, of course there should be electron accepting site. That basically makes sense. Like if some surface is just donating the electron, of course some surface should be there that is giving electron to it. So this is like common sense. But currently, according to the literature in specifically in CO2 hydrogenation, we are working. So in this field, in specifically thermocatalytic reaction, people just focus on the electron donating side. But now some people are thinking in this direction. So there should be some active side. There should be like oxidation site and reduction site. Electron donating and electron withdrawing site should be present there. And there is a one famous professor from MIT, and he is working on that. And one professor from the UK, this is Professor Hatching. He's very famous in the catalysis. He has around 50 years of experience. So he is trying to investigate that kind of concept. Like in a same particles, there should be active side for reduction and oxidation. So this kind of thing is possible, but still people cannot find it like on the experimental evidence based. But if there will be some progress, so I will inform at this platform.
Okay, thank you very much.
Thank you. Thank you. So any other question?
I have just some comments.
Please.
So thank you, Asif, for your wonderful presentation regarding the basics of catalysis. So first comment is for the fees. So when he asked like, can we change like the change in Gibbs free energy through the temperature or entropy? So yes, obviously you can change because delta G is related to enthalpy, temperature, and entropy. Like delta H is equal to delta H, delta G is equal to delta H minus delta into T into S. So of course, if delta H is positive, so you can manipulate like temperature or delta S, because for the reaction, you need to have like either delta G negative or as minimum positive as possible. So you can manipulate by rising the temperature, so it will make the second term negative, so it will like decrease the delta G. So yes, you can manipulate temperature, delta G, delta S to manipulate the change in the Gibbs free energy. So, second comment is regarding the Professor Bilal. So, what he mentioned, we can have like the same electron donating and electron withdrawing sides. So, on bi metallic catalysis, yes, there is some charge transfer from one metal to the other metal. So, which gives them like synergistic effect. Which means like if you are going to use monometallic catalyst, for example, tin along with the copper. So on tin, you will be getting some selectivity or conversion, or on the copper, you will be getting. But if you add both of them as a bimetallic catalyst, you will be getting like more conversion or selectivity rather than the individual ones. So this is called like synergistic effect, which happens due to some charge transfer from one metal to the other metal. And like one last point is regarding the surface area. So this is very tricky thing. If we are just referring to surface area, so the bigger particle will be obviously having the higher surface area compared to the smaller one. So if we talk about the specific surface area, which means like a surface area per unit weight of the sample or catalyst, so that will be obviously higher for the smaller particles. So this is actually very tricky thing. Those are all like comments from my side. Thank you.
Thank you so much, Lukman, for explaining in a very effective way and helping me. Thank you so much for wonderful explanations. So, any other question from Mr. Ravi?
Thank you, Asif, for the wonderful presentation.
Thank you.
Yes, everything is almost clear. Yeah. Could you clear like some points regarding with the turnover frequency? Yeah. Like how is
Please.
I couldn't catch few points, so can you just clear it much more clearly with the turnover frequency?
Thank you so much, Mr. Ravi, for nice questions. And so let me explain it again. So basically, like this is our particle. So if this is our active sites, so one molecule will come here, adsorb, and then there will be surface reaction, and then it will dissolve. So this is one molecule is got converted on one active site. So if we just start counting, and if in a 1 second, because this reaction are usually occurring in picometer or a nanometer scale, picosecond or nanosecond scales. So if we just count in 1 second, like how many molecules are converting from one active site, so this will be the turnover frequency. And this is in this way, and other way, like indirect method is we get total product, like how many amount of product is produced in 1 hour, and then we calculate the total number of active site in the materials, and then we calculate the number of molecules formed in 1 hour divided by 60 and divided by total number of divided by 3600 and into total number of active sites. So then we can calculate the turnover frequency in 1 second. Or if we just divide total number of molecule formed divided by total number of active sites, and then the answer will be the turnover frequency. So in this way, we can calculate like in a specific time, like in 1 second, 1 minute, or in 1 hour, on one site, how many molecules are get converted into the product. So this will be the turnover frequency. And then there is a turnover number. So turnover number is like catalyst is performing some reactions. So after some time, it becomes deactivated. So before the deactivation, this one site, how many molecule it can convert? Like 1 million molecule, 2 million, 3 million. So actually, and this will be the life of the catalyst. So actually, I have a different point from here. Like people say, our catalyst is stable for 10 hours, let's say. So if the turnover frequency for one material is 1 second and for other material is 2 seconds, so of course the total turnover number will be half, even though their catalyst is stable for a longer time. So this is most specifically like if we just go for the active sites, then we can clearly get an idea like how many molecule can be converted on a one active site before it go to the deactivation state. So this was the concept from this slide. Is it clear?
Yes, it's clear. So how do we really calculate the active sites, like in a real scenario? If you have some catalyst, and then if you want to know how much active sites it's been like does
Okay.
it carry? So yeah.
Yes, actually, this is like a topic for my consecutive talk for next time, but briefly I can explain here. Like if we have 1 gram of the catalyst, so we have some probe molecule. So if I want to see how many active site is for CO2 adsorption, so I will just take 1 gram of the catalyst and I will give it enough amount of the carbon dioxide, and it will be adsorbed on the catalyst surface, and then I can flow some argon and some other material at room temperature, and it will just go and dissolve. And then I can heat this sample, like all the unadsorbed molecule in the reaction system will be taken away by the some carrier gas. Only adsorbed molecule will be on the catalyst surface, and then I can slowly increase the temperature and they will dissolve, and then I can detect by the QMS mass spectrometer like how much amount of carbon dioxide is released from the system, and then I can count that number of carbon dioxide molecules, and that will correspond to the total number of active sites. So this is one of as an example, but briefly I will explain one by one in details in a consecutive meeting and how we can get the exact number of active sites. So this will be the process. Oh,
Okay, thank you.
thank you so much. So
Asif,
yes, please.
I am curious to know
Hmm.
when why the material become deactivated.
Yes, this is also one area that we will focus on the deactivation mechanism of the catalyst. Like this is like turnover frequency and number of active sites. So consecutively we will start this in details, maybe lead by some other expert, or otherwise I can carry on it. But briefly, I can comment in that, like we have some materials like iron oxide or some other material like titanium oxide or some other materials. So when we start a reaction, so there are many reaction intermediates. So some intermediate get reaction with the catalyst surface, and they cannot be dissolved, and then catalyst will become deactive. Like here I can explain a little bit. Like here, if we have a too strong adsorption of the molecule, so then if this will adsorb, so it will not dissolve and go to the surface reaction, so then catalyst becomes deactive, because if new molecule is coming, so no adsorption site is available. And second is if the product is too strongly adsorbed. So if the product is too strongly adsorbed at this, so this molecule cannot go to the product side, and then this chain will stop. But sometime it happens like if we have some intermediates, like if it go there, adsorb, and then it become into the atomic state, and this atomic oxygen usually like oxygen or some others, so they call some poisoning effect, and they become the part of the catalyst, and then catalyst composition is changed and it becomes deactive. Sometime like in biomass conversion or some others, we have some sulfur and hydrogen and oxygen, so it sometimes it becomes sulfuric acid or nitric acid and this kind of thing. So this can also deteriorate the catalyst surface and cause a poisoning effect, and it becomes deactive. So basically catalyst surface and catalyst composition is changed through the effect of this different intermediate, like high temperature, pressure, and this kind of things. So its composition and its surface properties change and it becomes deactive. So this is a brief comment, but we will discuss in detail one by one reaction processes and deactivation process, because this is also one of the most important concept in the catalysis.
Thank you. Thank you very much.
Thank you. So if there is no question, so maybe we can stop here, and then if you have any questions, so maybe we can discuss.